Now we are going to talk a bit something very tricky. It's not easy to imagine or speculate. Just uh, just assume we are doing the experiment. I cannot draw the column, so I'm just drawing something like a 2D image. Just assume we have a horizontal column, and then these are our packing materials. Just assume this is our packing material. Maybe can make it even a bit simple here. So this is our column. Just assume this is maybe some other image. Sorry. I don't know. I'm so bad in drawing. So let's assume this is our packing material. I'm drawing like this to make a bit more simpler. If not, it will go. It's very difficult to understand really. So just assume this is our column filled with our packing material. Obviously, in real world, it's not going to be like this. And then just assume we placed some very concentrated plug of our, we can call it as a concentrated Analyte plug. Let's assume we introduced the column inlet. All these words, concentrated, Analyte, plug, and all these buzzwords might look new to you, but these terminologies are completely fine, and they use it again and again. Especially the analytical chemistry people, they use these words often and so frequently. So let's assume we have a concentrated Analyte plug at the column inlet. Obviously, we are going to supply with pass our mobile phase. So to make this one easy, just assume this concentrated Analyte plug contains obviously like many number of molecules of our Analyte. At the moment we are assuming this is a pure compound, say like Analyte A. It can be paracetamol, for example. So once we supply the mobile phase, as I said to you, due to constant, it will dissolve your Analyte, and then the dissolved phase will go towards the eluent will go through the stationary phase until it reaches the column exit. So it's going to get adsorbed, say like it's going to get adsorbed onto one of this site, and then so just assume all these particles, these sites which I'm drawing now, they are your adsorbed analytes. How to draw the water on the top? So just assume we're continuously supplying the mobile phase. So I'm going to just look at the highlighter. Just look at the highlighter. Just assume these are the liquid which is flowing through the column. So at any instant of time, there will be some analytes in the liquid and some analytes in the solid. So they will be in equilibrium with each other. So there will be some analyte. So you put a point on. So this part or this part or this part or this part or this part. At any point, there will the concentration of analyte in the solid will be in equilibrium with the solution. So some analyte will be in equilibrium with the analyte in the mobile phase. So if you want, we can say like some analyte adsorbed in the solid phase, adsorbed in the stationary phase, will be in equilibrium with the mobile phase. So if you want, we can define, say like See, at this particular particle, or we can call it as an equilibrium stage. At this stage, the concentration of your solid, how do you call, concentration of your analyte in the stationary phase will be in equilibrium with the concentration of analyte in the mobile phase. So the ratio of these two will be like a concentration of stationary phase and the concentration of mobile phase. This will be equal to something called as equilibrium constant. Equilibrium constant. So if you go back to this figure which I showed here, so the molecules will move from, say, just follow the pink pen. The molecules will move from your column inlet to one of this spot, and then there it will establish an equilibrium with the solution side, and then it dissolve, it will move to the next spot, it will establish an equilibrium with the liquid side, and then move to the next spot, it will establish an equilibrium with the liquid side. Yeah, so there exists some series of adsorption desorption process which is going on, but at the same time adsorption is happening because there, and eventually it reaches an equilibrium with the liquid phase. Yeah, so unless there is an equilibrium, like the same analyte can never exist in two different phases, so solid and liquid. Yeah, so they exist in two different phases naturally, and that happens because there should be an equilibrium in between each other. If not, all the analytes will be in the solid phase or all the analytes will be on the liquid phase. Yeah, so keep those things in the mind. This is a basic chemistry concept. So we call this as an equilibrium constant, and we talked so far a lot about retention time. So typically if k value is higher, then retention time is higher. Say like you have one column, another column, another column. So we have analyte A, where we have analyte B, analyte C, and then we have the same mobile phase. So the retention time of, if the k value of A is less and k value of B is high, then the retention time of C will be higher. The retention time of A will be lower. So I hope you all understand up to this point. So what it practically says is like if k value is higher, it means your analytes are strongly adsorbed onto the solid phase, which also means like your analytes are preferential, highly, how do you call it, your silica particles are show some high level of binding affinity towards your analyte molecules. So that's why the adsorption is strong, and that's why your k value is higher. Yeah? So it also means like at equilibrium your solid particles can retain more amount of your analyte C when you compare it to analyte A. So that's the whole idea. Keep these things in the mind. So if k value is higher, it means a lot of things. One, it has a strong affinity. Your analytes are strongly adsorbed onto your silica particles, and if you see the concentration of stationary phase is much higher than the concentration of analyte in the stationary phase is higher than the concentration of analyte in the mobile phase. Yeah? I think I didn't confuse you. This is a bit tricky. Yeah? So keep those things in the mind. So K value is related to stationary phase, and how we have managed to separate the chromatography. Sorry, if how we separate, yeah, a mixture of compounds in a sample using chromatographic technique. Just imagine you have A plus, we have some concentration plug. So this contains A plus B plus C. So this is our sample mixture that contains A plus B plus C. So K have a retention, I don't know, adsorption equilibrium constant of say 1.1. B has a K value of K is equal to 1.9. C have a K value of say 2.2, something like that, for example. So once you pass your mobile phase, so K value, your analyte A, whose K value is 1.1, it should elute faster, yeah. So say like 10 minutes. So you can put a beaker and collect your compound A, and say this analyte B, whose K value or equilibrium constant is 1.9. So it will elute say maybe after 1 hour 60 minutes. So that time you can collect your compound B, and then say analyte C, which has a K value of 2.2, it will elute. All we need is to just continuously supply our mobile phase. Obviously it's going to go through a series of equilibrium stage. We will come back to that later, theory behind those things. So say it comes at 120 minutes. So that time we can put a separate beaker, and then we can collect our analyte C. Yeah, so these are nothing but elevate. So this elevate contains elevate in the third beaker contains your eluent plus pure compound of C, and this one contains eluent plus B, and the first beaker contains eluent plus compound A. We call them as elevate. So what it says is like compound A elutes first, compound B elutes second, and compound C elutes third, and that matches with their K value. So these are the things you have to remember. So we already learned a lot about retention time when we already talked a bit about the traveling time of each molecule, or the time spent by each molecule in the column, in the stationary phase to be precise. And then we also learned about adsorption, desorption, and it's not only about adsorption and desorption, that's the everything behind the separation, but it also happening, it's not like one time adsorption job, it's like it adsorb, desorb. So there are several equilibrium stages which is going on throughout the throughout the process. So keep these things in the mind, and then whatever we learned so far, we will try to connect it with the resolution, and then we will also try to connect it with the theory. If you want, we can develop our own theory, but it's not necessary because we already have some established theories to explain all the events which are happening in the column chromatographic separation process. Yeah? I think so far all good. Maybe I will cover one more topic for this lecture, and then I will explain everything in the next lecture. So what we are going to do, I already explained what happens when you say like we are dealing with analyte A. For the moment, if you start with one molecule, it's easy to capture the image. We already know once your mobile phase is going to carry this your analyte, and it's going to go here, it's going to go through a series of adsorption, desorption step, and it will elute out. But imagine if you carry, say this is your column, you have a lot of particles here, lot of silica particles, and just assume we have, say like I'm going to draw something like a small beads, so they are like a filled ones. Just assume they are your analyte particles. Say we have I don't know how many numbers we have, 1 2 4 7 9, 10, 11, 12, 13, 14, 15, 16. So we have just assume we have 16 molecules. So this is only to get some idea how the chromatography works. So once we supply our mobile phase, it's going to dissolve all your analyte, and then it's going to move towards the column. So I said to you, what happens is your solution front will be exposed to silica particles which are free of your analyte, so naturally your adsorption will happen. So let's focus only on this part of the column. So these are your silica particles. So just assume they will adsorb onto this one, adsorb onto these particles. So just assume all the silica particles are enriched with your analytes. But at the same time, so this front of the eluent which is moving towards the column exit is always exposed to fresh silica particles. So which means there also exists some concentration gradient between this silica particle which is already adsorbed with your analytes and the silica particles which is somewhere here in front of this flowing analytes. So due to this concentration gradient, your analytes will move from this side to this side. Some will move from this concentrated zone to the front side of your chromatography column. And we all know, like we are continuously supplying the mobile phase, so which means you are going to continuously desorb. So at the back side of this concentrated plug, we can call it as an elevate plug. At the back side of this elevate plug, you will have these silica particles free of your solute molecules. So these particles are free of your analyte molecules. Yeah. So let's follow the arrow here. Just follow the break. I took a lot of break while I'm recording this lecture because this is so time consuming and giving me a lot of headache, honestly. Yeah. So I'm going to edit this video before I upload in the YouTube. Yeah. So because these are very tough concept, you have to have some clear imagination. Yeah. So just to follow the blue line, blue arrow. So blue part, blue ink. Just assume these are your silica particles free, which are already you knocked those adsorbed particles and now they are free of your analytes. But just imagine, I said to you, diffusion will happen if you have a concentration gradient. Yeah, so nobody have to push the molecules to move from a high concentration zone to low concentration zone. It will happen naturally even if there is no external force like agitation or maybe some extra bit of pressure or something. It will happen naturally. So just to follow the blue pen. So even if you have a concentrated elevate plug at the middle of your column, your adsorbed solute particles will slightly diffuse back to this silica particles which are free of your analytes. So they will slightly diffuse back. So some of these silica particles will again be adsorbed onto the with analyte particles. Yeah. So analyte molecules. Sorry, keep those things in the mind. So what we are learning at this moment is like, no matter, say at time t equal to 0, say like we place a very concentrated plug of analyte molecules. Say this is an analyte plug, highly concentrated. So this is nothing but the plant extract or a pigment placed by the Michael Sweat in his own experiments, yeah, in the very first column chromatography experiments. So let's call it as analyte plug, and let's say this is highly concentrated and it contains only analyte A. So no matter if you put a very concentrated plug, it won't move like exactly the same way. Like this concentrated plug won't move just like that, something like this. No, this is a no way job. It won't happen just like that. So it won't happen like that, and that's because we have a sequence of operation. One is adsorption, and then it also your molecule will move from solution side to the solid side via diffusion, and then something will, I said to you, if you have silica particles, it will move something to the back due to the, because there exists a concentration gradient between this concentrated plug here, which is located at the middle of the column, to the back side of the, to the, how do you call it, to the back of this concentrated plug, to this side of the silica particles, due to via diffusion, again due to concentration gradient, and some molecules will move towards front because these particles, how to say, like, so if you, even if you if you start with a concentrated analyte plug somewhere in the middle of the column, just to say these are your silica particles, all adsorbed by your analytes, some will diffuse forward somewhere here, and then some of the solute will also diffuse back due to, because there exists always some concentration gradient. But still, since we are supplying the mobile phase continuously, this whole process will move towards in only one direction eventually, and then it will reaches to the column exit. So why we are talking all this blah 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 for the last 10 minutes is like because we are going to discuss something very peculiar to column chromatography experiment. So if you started with a concentrated analyte plug, I said you will have some concentrated zone here, and then some less concentrated zone here, and some less concentrated zone back, which are already adsorbed onto the silica particles, and eventually all will be knocked out via diffusion, and then eventually it will reach the column exit, which is here. So just assume if you put a detector here, the purpose of detector is to check the concentration of your analyte. For example, we can put an EV spectrum photometer. You put an EV spectrophotometer. I know you might get angry by listening to this lecture because it might sound so funny or maybe too basic for you, but at the end of the day, when you're going to discuss the chromatography theory, these are the ideas, or these are the pictures that should come to your mind. So we have so many parameters in those equations, and everything is related to something what we are seeing, and also the experimental outcome will if you want to understand the experimental outcome, you have to understand what we are talking at the moment, right at the moment. Yeah? So I'm going to change the color a bit. Teaching chromatography is a pain, like it's not easy. So just assume these are your analyte particles, the pink colors ones, pink color ones. Yeah? So if it is imagine like let's say a crude experiment. So this time there is nothing in the column, so its column is completely free. So you put your mobile phase, and then you put the detector in the say at the exit, at the column exit, sorry. So, and if you check the concentration here, so it will move immediately, instantly. Yeah? So if it will move instantly, and then if you check the concentration with respect to time, say with respect to time, say let's start something, say so a time we will see say like a time 1 minute time when time is t is equal to 1 minute, you will see some small concentration here, and then at time t equal to 1.1 second, a big concentration here. So just we don't have to mention whether it's in grams per liter or not. If the peak is high, which means the concentration is high. So which mean we can call it as arbitrary units on the y-axis, and then at say time 1.3 again some small concentration, and then nothing will happen after that. So what happens is like you manage to move the concentration plug, so somehow you manage to retain the shape, so it goes intact. So but if you plot time versus concentration, instead of one single peak here, still we will see some small distribution of concentration. And this is a empty column, so all we are just moving is we are moving our analyte using the mobile phase to the column exit. So even for this type of a simple process, instead of if you put your time versus concentration, if this is a concentrated peak, yeah, say like maybe I can put it separately. Let's assume we have here 1 2 3 4 5 6 of our analyte molecules, and then if you pass a mobile phase, it will move something like that. Something like that. And then once you put the time versus number of molecules here, say at time 1 minute you will get say 2 molecules, so 1 and 2, and then at time 2 you will get 1 2 and 3, say for example, and then at the time t is equal to, after some time you will get only 1 molecule. So in total we have 6 molecules. So even if we inject 6 molecules at one time, something like that one here, and in an empty column, all we are doing is we are just supplying a mobile phase, you will observe something like this, yeah, some graph like that. If you plot the time versus number of molecules, this is how we are going to observe a distribution rather than a concentrated plug, something like here, yeah, time versus concentration. And in this case what happens is like this is connected to molecular diffusion, so solute will diffuse from one side to another side. So there exists a concentration gradient, so and this concentration gradient can allow us to dissipate the concentration of your analytes within the solution. This is something related to molecular diffusivity. Yep. Something like that also happen in your column. So why we are discussing all these things? In the column, this is what exactly is happening. In fact, it will be even extreme case. Yeah? So even if you start with say 1 2 3 4 5 6 7 8 or 9 10, say like we are injecting 10 molecules, like a concentrated plug of analyte A, your mobile phase will obviously dissolve, and then it will get adsorbed, say 1 2 3 4 and 5. So there will be some concentrated region in the silica particle, because your mobile phase is continuously pushing your solid molecules to the other side of the column, and since the solution front is always exposed to pure silica particles, some will diffuse. So you will have few molecules in the front, and then it will also diffuse back, because we already dissolved these silica particles, so dissolve the analyte from the silica particles, so something will diffuse back because there exists some concentration gradient. So if you just imagine, we have a super sophisticated detector that allows you to count the concentration of your molecules. So if you plot a time versus number of molecules of A, so a time say like 1 minute, so you might get say 1 molecule, time 2 we will get 2 molecules, time 3 we will get say 4 molecules, and then say after some time you will get 2 more molecules, 1 2 3 7 8 9. So something like you will, and then you might get 1 more molecules. So, and this is not something like I'm drawing, because I'm trying to explain you, it's not true. This is what exactly happened when you perform an experiment in the lab. So if you connect them, you will get a Gaussian distribution. So the experimental outcome from a chromatographic experiment will always have a Gaussian distribution. Time instead of number of molecules. Here I just put number of molecules only to explain the concept. So we will have a, just put concentration here. So we will have a Gaussian distribution. No matter, you say like you, even if you inject time versus concentration, even if you if you place a concentrated plug at the column inlet, when it exits the column, you will have a Gaussian distribution. This will happen for Analyte, and this. So I hope you all understand. Yeah. I think this is fine so far. And okay, at the moment I just showed what's really happening. So at the moment we connected something related to molecular diffusion, and based on that we explained why we have a Gaussian distribution at the column exit. So keep those things in the mind, and in the next lecture there are more reasons to, this is one of the many reasons we have a Gaussian distribution at the column exit. There are more than one reasons that we will see this type of Gaussian distribution, and sometimes this distribution will be very narrow, sometimes this distribution will be very broad, and so on. So we will try to explain why, when the distribution will be narrow, and then when the distribution will be very broad. Yeah. So these things we have to learn before we are going to talk about resolution and also adsorption theory. So I can quickly show something a bit more before finishing this lecture. So just assume you have A plus B, like we have a mixture of that contains two compounds, A and B. So and we supply the mobile phase. So eventually it will transfer, say like this is molecule A, and then so this is molecule B. So with respect to time, molecule B will exit, and if you plot, say like, you will get this is for B, and then you will get something for A. So this is like a clear separation. And this is happening due to this adsorption effects and the mass transfer effects, which we already discussed. And then and if you look at this image, so we have two narrow distributed curves. So and that's why we are calling them as this. There is a clear separation. So but there can be another cases, like imagine you do the same experiment, A plus B, plus you supply the mobile phase. So this is our compound A, and say this time they are very widely distributed. So this is compound A. Let me change the color for compound B. Say this is compound B. So if you plot the time versus concentration, you will see some curve like this. Yeah? So this is for compound A, and then let me change the color, maybe see, I don't know, and then so this is for compound B, this is for compound A. So let's say this is B, this is A. So what does this mean is like at some time interval we get a mixture of A plus B. So there is no clear separation at some time. So normally we say this is like a poor resolution. Poor resolution, and normally we we already know why this spread happens. That's what we learned in this lecture. So try to keep those things in your mind. And then I'm going to upload some book chapter that, because I used a very like a normal dialogue, yeah, I didn't use any scientific terminologies or something like a professional quality that allows you to to remember and then read and write in the exam. So I'm going to upload some book chapters that you can use it as a guideline. So follow the lecture and also read the chapters in the book. So that's all you have to do. If you want, you can tell the book name. Coulson and Richardson, volume 3. It's a very good book. You can learn a lot about chromatography in this book. Apart from that, I'm using some specialized book on chromatography. I used a few more books, even some handbook on chromatography. So I won't recommend you to read all those books for this one particular chapter. So just listen to these lectures and then read the book Coulson and Richardson. That should be more than enough. Yeah. So for the exam, you will solve a few problems. I will try to solve maybe 3 to 4 problems, or maybe even more. I will show some graph, some experimental result, and then based on that graph, I will try to get some useful parameters or make sense out of those experimental results. Yeah. Okay. So before that, so I think you all understand up to this point. We already talked a bit about retention time, mass transfer, diffusion, adsorption equilibrium, and adsorption equilibrium is also happening at different stages inside that column. And then we talk a bit about molecular diffusion, and then we talk a bit about how the molecules move from high concentration zone to low concentration zone, and we talked a bit about the even if you supply a concentrated Analyte plug at the column inlet, the column exit, you will have a Gaussian distribution. So Gaussian distribution is the expected result out of a chromatographic experiment. And then I already said, based on retention time, based on equilibrium time, how your retention time is related to your equilibrium constant, and equilibrium, depending on equilibrium constant, we can separate the different compounds. Yeah, so your equilibrium constant dictates how good the chromatographic technique can be. Yeah, if you have to separate some compounds. And also another clue is something like your equilibrium constant will vary with your solvent. So if you use acetone, and if you think the equilibrium constant for some analyte A for acetone, I can draw it here. Say like say for we have analyte A, or maybe just say paracetamol for example. So if you use water for example, this is our solvent, and then say we are using silica particles. If the K value is say 1.2, and then if you use paracetamol, this time if you are using a mobile phase water plus another solvent, and then again we are using the same stationary phase, that K value will be different. So we can adjust. So imagine if we have say like A plus B plus C, and then if we cannot separate A plus B, which means the K value of A and K value for B must be almost closer to each other. So in that case, we can change the solvent. If we change the solvent, this K value is related to concentration in the stationary phase and concentration in the mobile phase. So if we change the mobile phase property, we obviously change the K value, which means we are going to change the retention time. So that way we can manage to improve our separation efficiency. I hope you all understand up to this point. So I'm going to stop recording the lectures now. Try to go through these lectures a bit slowly. I know I explained it very slow, but that's okay. Chromatography is not an easy process to read everything quickly by reading 2 or 3 pages and come to a conclusion. It is a tough process to understand, but an easy process to perform. Yeah. So thanks for listening.